SwayamPrabha. Digital India. Educated India.
Welcome back to week 2 of the course, where we will discuss about the mechanical response of polymers. So, we will learn that this mechanical response mainly depends on both temperature as well as time. In this video, we will focus on the temperature effects, and in a later videos we will look at the effects of time as well. So, first let us see how the mechanical behavior changes with time. For this, let us first discuss about the metals, and then we will discuss for polymers. For metals, we know that the melting point is usually high. So, it is 660 degrees centigrade for aluminum, and for steel it is about 1400 degrees. So, as you can see, these melting point temperatures are very high compared to the room temperature. Room temperature being somewhere between 25 and 30 degrees centigrade, these temperatures are very high. So, even if there is a small changes at room temperature, so from room temperature let us say it goes to 50 degrees centigrade or 100 degrees centigrade, these small changes are still very far from the melting point. Therefore, the behavior varies negligibly. So, which means let us say at room temperature aluminum and steel, they show a ductile behavior, but if you increase by a 50 or a 100 degree centigrade, this linear elastic behavior is still there. Maybe there are small changes which are very negligible, but let us say from room temperature we go closer and closer to the melting point. How does the behavior of these metals change? Now there is a new phenomenon called creep. Probably you are aware of creep, but what is creep behavior? So, let us say we have a rod made up of steel, and which we are holding at the top, and at the bottom we apply a dead weight meaning a constant load. So, the moment we apply the load, there is instantaneous deformation because of the elastic behavior, but then if we leave it there for a long time, so this deformation instantaneously probably is some delta, but if you come back after a minute, this still elongates, and if you come back after an hour, a day, a month or a year, this continues to elongate. This is called as creep behavior, which means it is a time dependent phenomenon. But at what temperatures do we see this creep behavior for metals? We see it when it is approaching the melting point. So, for aluminum and steel, let us say if it is like 100 degrees below these melting point temperatures, that is where we see this creep behavior. But now moving into polymers, let us see how these behave at room temperatures and how sensitive they are for changes in the temperature. So, usually the glass transition temperature is the more important temperature when it comes to polymers. So, unlike metals where we discuss about melting point, for polymers we discuss more with in terms of glass transition temperature or TG. So, usually it is not too far from room temperature, because let us say when we are discussing about PMMA, which is plexiglass or polystyrene or thermocol, these the TG is around 100 degrees centigrade. But if you are talking about thermoset polymers like epoxies, which are mostly used in structural applications, even there the TG ranges, but on an average it is about 80 degrees centigrade. So, what do we see? That this glass transition temperature compared to room temperature, it is not too far, because room temperature, even if we say is 30 degrees centigrade, these are just like either 50 or 70 degrees apart, which means they are very close to the glass transition temperature. So, because of this, the mechanical behavior varies significantly even if there is a small changes in temperature. So, from room temperature, let us say the temperature changes either increases or decreases by either 10 or 20 degrees centigrade, that is a significant amount. The reason is because now we are talking about temperatures which are very close. So, what we are seeing here is for the metals, the slight changes at room temperature does not really affect the mechanical behavior, but for polymers slight changes at room temperature do affect the mechanical behavior because we are very close to the glass transition temperature. Now, we will see how the stress strain behavior changes for different polymers. So, in this stress strain plot, we see that there are 4 different curves, and these 4 different curves, each of them signify a different mechanical response or a mechanical behavior. So, we will start with brittle behavior, so which is shown here. So, this is shown by mostly crystalline materials or networked polymers like thermosets such as epoxy and polystyrene. So, here we see that upon loading the behavior is elastic, but failure happens suddenly, which we all know is the definition of brittle behavior. Then the second one here is the semi-ductile. We call it semi-ductile because now it can take more larger strains, but it also shows this yield behavior, but the failure strain is not very large. It is certainly more than brittle, but not comparable with ductile materials, which we will discuss next. And this semi-ductile behavior is shown by PMMA, the plexiglass, which is a thermoplastic. So, the third one is the ductile behavior, which is shown by again polymers such as polycarbonate and PET. PET is the plastics mostly we use for water bottles. So, as you can now see, there is a large strain before failure, but then even the stresses are reasonably higher. But the last category are elastomers, where it shows a very large strain before failure, but in addition to that the stresses it can take are very less. So, the classic example is rubber, either natural or synthetic rubbers. These can take very large strains as much as 300%, but the problem compared to other kinds of polymers is the kind of stresses they can take are limited. So, what we have seen is there are polymers which behave either brittle, semi-ductile, ductile or elastomer, and what dictates whether a polymer behaves as a brittle, semi-ductile, ductile or elastomer is what we will see in the next slide. So, previously we discussed about the glass transition temperature using this volume versus temperature plot, and we said glass transition temperature is the temperature at which the free volume is negligible and then the polymer transforms into a glassy state. But now what we are trying to say is the response depends on how close the temperature is. So, we are talking about operating temperature, which can either be room temperature when we operate, or maybe there are some applications where the operating temperatures might be either high, such as components close to engine, or the operating temperatures can be cold, like let us say we an automobile working in sub-zero climates. So, which means that the response greatly depends how your or how close or how far the operating temperature is from the glass transition temperature. So, a better measure to look at this is the ratio T by Tg. So, your operating temperature by the glass transition temperature. This ratio will help you to understand how the polymer behaves. So, whether this T by Tg less than 1 should be in the left direction, and these are when T by Tg is greater than 1, and this is when T by Tg is less than 1, and this is when T by Tg is equal to 1. So, that is how we normalize the x axis here, saying that at glass transition temperature we will equate to 1, and to the left we have things which are less than glass transition, and to the right we have more than glass transition. So, let us look with a couple of examples, starting from brittle behavior. We notice brittle behavior when this value is about 0.75. So, 0.75 will be somewhere here, let us say. So, which means we are looking temperatures less than the glass transition temperature, where the behavior of the polymer is glassy, as we have already seen it in previous discussions. So, the kind of polymers which exhibit this behavior are these plexiglass as well as epoxies. So, now let us look at behavior when this ratio is 1. So, which means the operating temperatures are about the glass transition temperature. So, that is when the mechanical behavior is termed as leathery. What we meant by leathery is when the polymer is very soft and it can deform by a greater extent compared to brittle materials. So, polyethylenes, especially the low density polyethylene, behaves leathery because the glass transition temperatures are very close to room temperature. So, lastly we will look at rubbery behavior. This we notice when this ratio T by Tg is about 1.5, which means we are somewhere here on this plot. So, since we are above the glass transition temperature, which means then there is the secondary bonds are broken, as well as we have the free volume. This allows the polymer chains to slide over each other. This gives us the rubbery behavior. So, this ratio T by Tg can help you define how the mechanical behavior of a certain polymer is. Now, we will move into seeing how the modulus, which is a measure of the stiffness of a material, changes with temperature. So, for this we will take an example of amorphous polymer. So, the examples are like plexiglass and polystyrene. So, this figure shows on y axis the modulus and on x axis the normalized temperature. As we just defined, normalized temperature is a better way to represent polymers, because then at 1 we know it is at glass transition and we expect some major changes to happen in the polymer. So, bear in mind that the y axis here is a log scale. So, you have this 1000, to the left we start close to 1000 megapascals and we reduce as much as 10 power minus 2, which is 0.01 megapascal or 10 kilopascals, and the temperature are in the range of 0 to 2 normalized temperatures, which are the ratio T by Tg. Okay. So, as we can see that the modulus varies significantly. How significantly? It started from 1000 megapascals to all the way to 10 kilopascals. So, it is several orders different, or the changes are by several orders as the temperature changes for a specific polymer. For example, here it is PMMA. But let us see with modulus changes we can define different regimes in this polymer. So, which means the response in one regime is very different from the response in the other regimes. So, in fact, there are 5 different regimes we can identify for this polymer. So, we will go one at a time. First is the glassy regime. First is the glassy regime, which is somewhere from the start to this. So, this is the glassy region. As you can see in the glassy region, the modulus is very high. It is in the order of 3 gigapascals. But as you increase or come close to the glass transition temperature, that is when we see the second regime, which is the glass transition regime. This is also called as viscoelastic regime. So, this is where the viscoelastic behavior of the polymer is most seen. So, it is also called as viscoelastic transition regime. So, this is again between so and so. So, starting from the end of the glassy regime is the viscoelastic transition regime. Let us say this is glass transition. But if we further increase the temperature after this glass transition regime, that is when we see the rubbery behavior. So, between this is the rubbery behavior where you can see that the stress values are more or less constant, or we see a plateau in this plot. But after the rubbery behavior, when the temperature is further increased, that is when the polymer behaves as a fluid or viscous flow. So, this is termed as the viscous regime, where once you increase the temperature of the polymer, it basically melts and it is flowing. So, this is good let us say for thermoplastics, because once it flows, it can be remolded into a new shape. But in the case of thermosets, where we have heavily cross links, this viscous flow is not seen. Instead, if we further increase the temperature, we expect to see this decomposition. What is decomposition? Where the polymer chains, the primary bonds or the covalent bonds, we have sufficient energy to break those bonds, and then the polymer decomposes, which we also call as depolymerization. So, it is not shown in this diagram because this is an example of an amorphous polymer, but decomposition usually happens in thermosets. Yeah. So, what we will do now is go into each of these regimes and look at more details about how the mechanical behavior varies with each other. So, we will start with the glass regime. So, this is a picture about how we can visualize the glassy regime. So, what we see here on these dark blue lines are the primary bonds or the covalent bonds, and these dots are the subgroups or the radicals. Like for example, in polyethylene, these small dots are nothing but your hydrogen atoms. Okay. So, what we are trying to show here is that there are multiple polymer chains all together. So, again to remember you, we are discussing about amorphous polymers. Amorphous polymers means there is no crystallinity. So, we do not expect to see them coming neatly each other, but we see these chains are random. So, when do we see this glassy region? We see it below the glass transition temperature. So, we already know that if it is below glass transition temperature, the molecular packing is tight, which means these molecular chains are close to each other, and that is when we have these secondary bonds. What are the secondary bonds? Let me change the color, let us say with red, let me show this. So, the bond between these two hydrogen atoms in for example of polyethylene is the secondary bond. So, like this all throughout the polymer there will be several of these secondary bonds. These are all formed because now the polymer chains are close to each other. When they are close to each other, because of the proximity, there are bonds like either hydrogen bonds or van der Waals forces, which are all secondary bonds which are formed, and these help the polymer to give good mechanical behavior or stiffness to the polymer. So, we already mentioned that we see both the primary bonds and the secondary bonds. And what happens when we stretch this polymer in the glassy region? So, it stretches elastically, because when we load, both the primary bonds as well as the secondary bonds will resist the deformation, which means they are taking loads. So, it is not just the primary bonds, but also the secondary bonds, that needs to be kept in mind. So, there is one more important phenomenon which happens in the glassy region. So, this is again the modulus temperature plot from the previous slide, but here we are only focusing on temperatures less than glass transition. So, we are focusing on less than 1 of this normalized temperature. So, what we notice is there are some interesting features called as secondary relaxation. So, for example, if you notice here, there is a slight dip in the modulus. Similarly, somewhere here too you can see there is a slight dip in the modulus. Though in this figure it shows as a slight dip, bear in mind this is a log curve. So, which means this can be almost like half the initial value, because now we are talking about 1000 megapascals or 1 gigapascal. So, from 1 gigapascal, let us say it drops to 0.5 gigapascal. Here it might look like a small drop, but the actual values are large. But now let us understand why do we see this secondary relaxation. What is the molecular reason for this? So, this is due to few loose sites. So, every time in a polymer it is not like the density or the packing is homogeneous throughout. There are always some loose sites, especially in some pockets of the polymers, where once you slightly increase the temperature, there is enough thermal energy for these loose sites to readjust. When these loose sites readjust, they give this extra strain, and because they give this extra strain, the modulus or the stiffness decreases. So, these are what we are seeing it as secondary relaxations. These happen in the glassy region, and the reason why we are discussing more about it is because the variation in the modulus values are high. Okay. So, as I mentioned, the modulus drops at most to half or even more in some instances. But now let us see from this framework of this glassy regime, is it possible for us to estimate the modulus of these glassy regimes in terms of again the primary bonds and the secondary bonds. So, for this we will start by introducing this fraction called the fraction of covalent bonds. So, we said this polymer has both primary bonds and the secondary bonds. So, we are saying F is only the fraction of covalent bonds. So, which means covalent bonds by covalent plus secondary bonds is nothing but our fraction F. So, of course, when we define it this way, what is 1 minus F? It will be the fraction of secondary bonds, because which is secondary bonds by addition of both covalent and secondary bonds. We also define these terms E1 and E2, E1 being the modulus of the covalent bonds. So, let us think of an example where we have 100% covalent bonds. Can you think of any polymer or any material where there are just covalent bonds, but there are no secondary bonds at all? So, one example for that is diamond. So, where we have strong carbon bonds in all directions. So, for diamond the modulus falls about 1000 gigapascals, that is what we are seeing here. But the other extreme is an example where we find only secondary bonds and either 0 covalent bonds or very few covalent bonds. So, the example for this is paraffin wax. So, the wax used in the candles or maybe the wax used in even the crayons. These are made up from petroleum product, but these are mostly secondary bonds, that is the reason why they are very soft. So, for these the E2 value is about 1 gigapascal. Okay. Now, we have defined this fraction of covalent bonds, and we said we also have this E1 and E2 for covalent bonds modulus and secondary bond modulus. Now, let us try to see if I have a polymer like this and I apply a load, what will be the strain in this polymer. So, the strain I can write it as a summation of strain which we see in the covalent bonds plus the strain we see in the secondary bonds. So, this is written by this equation, but before we get overwhelmed, let us look one at a time. So, the F here is showing us the fraction of covalent bonds, and what does sigma by E1 show us? Sigma is the applied stress and E1 is the modulus of the covalent bonds. So, sigma by E1 should give us the strain from the covalent bonds. So, what is this? This is strain from covalent bond. Similarly, now let us see what is 1 minus F. We already showed here 1 minus F is nothing but the fraction of secondary bonds. So, these are the fraction of secondary bonds, and sigma by E2 will be the strain from secondary bonds. So, what we are basically doing is the total strain. Total strain is the summation of strain from covalent bonds plus the strain from secondary bonds. So, we are multiplying with the fraction of covalent bonds and the fraction of secondary bonds to get the actual or the total strain. So, of course, we can simplify this because we see on both terms we have sigma in the numerator. If we take it as common, we should be able to write it in this form. So, what have we achieved now? We are able to write the total strain as a function of the applied stress times F, E1 and E2. Okay. From this, can I now estimate what is the modulus of this polymer? Yes, because modulus is simply the ratio of stress by strain. So, the modulus is simply stress by strain. If the ratio of this stress by strain is nothing but inverse of this component. So, we have this F by E1 plus 1 minus F by E2 in the inverse. Please note that we have an inverse here and then it makes sense. Okay. So, this is just an equation, but for us to get a feel of what this equation represents, now let us plug in some numbers. How can we start? We can start with this E1 and E2, because we already showed that in extreme values the E1 becomes 1000 gigapascals and E2 is 1 gigapascal. So, once I substitute this, then the modulus is simply a function of F. What is F? F is the fraction of covalent bonds. So, which means I can go the values of F from 0 to 1, 0 meaning there are 0 covalent bonds, which means it is a pure secondary bond material like this wax, and when F is equal to 1, which means it has only covalent bonds, and that extreme is the diamond. So, let us show it with a plot here, where as I just mentioned this is F equal to 0 and the other extreme is F equal to 1. So, F equal to 0 we have this paraffin wax, and F equal to 1 we have this diamond, where the modulus as we showed is 1000 gigapascals, and paraffin wax it is around 1. Again I need to remind you that the y axis again here is logarithmic. So, it is a log scale. So, meaning from 1000 to 1 we are going one order at a time. Okay. Now, let us take few polymer examples and see where they fit in this curve. The curve what we see here is simply a plot of the formula what we see here. But now with examples, let us see where few polymers lie on this curve. So, we will start with amorphous polymers. The examples of amorphous polymers are PMMA and polystyrene. For these, the fraction is somewhere around 0.5, which means they have equal number of covalent and secondary bonds. So, when we have this 0.5, our modulus should be somewhere here, which falls out to be 3 gigapascals. So, we said this is the point where we have amorphous polymers like PMMA and polystyrene. When do we have this fraction more than 0.5? That is when we have more and more of these cross links. So, for thermosets. So, for thermosets we have highly cross linked examples are like epoxies and others, and then these value of F can increase to 0.75, which means we are looking at somewhere here the corresponding point is somewhere here, we are calling this as for epoxy or other polymers, and the corresponding values we will see that it is still less than 10 gigapascal, somewhere around 8 gigapascal. Can you think of any polymers where this fraction is beyond these values, so much more than 0.75? So, we are now talking about polymers where they have predominantly covalent bonds and very few secondary bonds. So, though I showed you an example of diamond, it is not a polymer, but for polymers one example of this is fibers. At first it might be difficult for you to understand why we call fibers where the fractions are more than even 0.9, but the moment you notice that how do we form fibers? Fibers are formed either through extrusion, which means you through a small orifice you pull out the fibers. From the other end is the molten metal, and through an orifice you pull out the fiber. But what is happening while you pull out? While you pull out, all these molecular chains are aligned in the direction of the pull. So, which means all the molecular chains, what do we have in the molecular chain? The backbone carbon primary bonds or the covalent bonds. So, in the direction, let us say this is the fiber and we are looking in the direction of the fiber, all the molecular chains are aligned. So, this value of 0.9 is only in the direction of the fiber. But if you are looking at directions perpendicular to the fiber, that is when we will find most of these secondary bonds, and this value of F will be very small. But now let us focus on what happens when this F value is very high. From this plot you can see that it can be somewhere here. So, which means we are talking about 100 gigapascals. So, this is where we can have nylon or Kevlar fibers. And this should explain you also the reason why people use these Kevlar fibers, carbon fibers or glass fibers in composites, because these are really strong and stiff along the direction of the fibers. Perpendicular they might be weak, but along the fibers, though it is made up of the same material, once you draw them into fibers, they are extremely stiff and strong in this direction, mostly because the loads are taken by the covalent bonds or the primary bonds. Okay. So, with this let us summarize what we have discussed in this video. We started by saying that the mechanical behavior changes with temperature. We started by metals saying that the melting points are high, but when it comes to polymers the glass transition temperature is very close to room temperature. So, even with small changes of temperature for polymers we expect large changes in the mechanical behavior, but for metals even though changes are small at room temperature, usually they do not affect the mechanical response significantly. And we also have seen that it is better to talk about this temperature dependence in terms of this ratio T by Tg, where Tg is the glass transition temperature. And we also have seen that polymers exhibit different kinds of mechanical behavior, such as the brittle behavior, semi-ductile, ductile and elastomer. It all depends on how the polymer packing is and what is the kind of bonds we have between the molecular chains. So, taking an example of amorphous polymers, we said that it shows several regimes. Here we are listing out 5 different regimes, starting with the glassy regime and then the glass transition, rubbery, viscous and finally the decomposition, polymer decomposition. In this video, we were able to discuss more about the glassy regime, where we said that the chains are tightly packed and we have these secondary bonds between these molecular chains. We have also looked into these secondary relaxations. These are relaxations because of the loose side. The moment the temperature increases, these loose sides readjust, and because of the readjustment they give extra strain, and that leads to a slight decrease in the modulus. Though we say slight, actually in terms of values it is large, and that is why it is important for us to look at secondary relaxations. And later we said, in terms of the fraction of covalent bonds, we can derive a formula, or we showed you a formula how to estimate the modulus of a polymer. And using several examples, we have shown how the fraction f determines the modulus, whether if it is at around 0.5, we are talking about 3 gigapascals, but if it increases to 0.75 in terms of thermosets, the modulus increases to 8 gigapascals. But in conditions of fibers where this fraction is more than 90%, that is when we get a very high modulus in the order of 100 gigapascals. So, in this video we only focused on the glassy regime. In the next video we will continue with the remaining 4 regimes. See you later. Thank you.